These loops are next to go. There's an awful lot of them going on here, and as I've mentioned before, algorithms are a better choice than hand-rolled loops because they're more immediately readable. And in many cases, we're going to make our code a lot smaller by ripping out hand-rolled loops and replacing them with an algorithm. Let's put the right include up at the top here. I'm going to start with this pair of loops that iterates through printing out the values at each element in what was once an array and is now a vector. I'd like to replace the language for, which could be doing anything, with the standard for each. So the for each doesn't take this syntax that the for loop has. Instead, we want to do it to the whole collection. This is numbers, so we'll go begin at numbers, end at numbers. And what do we want to do? Interestingly, if I only just wanted to print the numbers out one per line, this would be less work, but let's keep the exact same functionality. The functionality that we have is also printing out this sort of index. What I'm going to do is move this declaration of the index here. For my third parameter, I'm going to use a lambda that will capture that index by reference. Now the lambda is called by the for each and it's passed an element of the vector for each time we go through. Closing off the lambda, and that closes off the call to the for each. I need to increment that n as we go through each time. It starts at 0, but we wanted the output to come out saying 1, 2, 3, 4, 5. So the simplest thing for me to do is to increment n, which we captured by reference, each time I go through, and to increment it before using it. So it's going to start at 0, I'll increment it to 1, print out 1, will be great. Now I can't say numbers at n anymore. Instead, I'm going to use the element I was passed. This loop takes up about the same amount of stuff on the screen as it ever did. But as I told you in the algorithms section, the benefit is you know when you read these letters, this goes through each element exactly once. There's no tricks in here that skip ahead a few or that go back up and do another one again or anything like that. It does something to each element exactly once. As you get used to reading code that has algorithms in it, that, oh, I don't need to look through the loop and figure it all out, will start to become apparent. I'm going to do the very same thing to our animals code. Begin at animals, end at animals, a lambda that captures m, a string called element, beginning of the lambda, end of the call to for each. I'm going to increment and then use the m that I captured, and here I'm going to print out the element. Where things get fun is a loop like this. This particular loop is actually demonstrating the use of a function pointer. Operation here, if I hover over it, says typedef int, you see lots of brackets, lots of stars, that's a huge clue that something is a function pointer, is equal to addition. And sure enough, addition is a function that takes a pair of integers and returns an integer. So this code is setting up a function pointer and using it here inside this loop to iterate through and add all of the elements of the array. Well, I have a much quicker way to do that. I'd like to use an algorithm called accumulate. Now, this is not in the algorithm header, so I need to come up here and include numeric. then I can just write this. Total is equal to standard accumulate at, like so many of these, it takes a range, so we can go from the beginning of numbers to the end of numbers. By default, it just adds them all up. And all I need to pass in is the starting value. Just as we had 0 here into total equals 0, I can actually just do this. I'll comment out these lines, declare int. Now our for loop completely evaporated. I know what you're thinking. Maybe I wanted a function pointer there. We'll come back to that. For now, let's see if this code works. I commented out the declaration of op. This all looks exactly the same, even though it's now using a for each instead of the standard for loops. And the total, if you had it memorized between versions, is the same total as before, 2257. I like this single line a lot better than these lines here. They need less explanation. You can remember what accumulate does. You don't have to read through to try to understand every word of it. If you think you're giving up power or capability, what if I wanted to add them up in an odd manner using that function pointer? Let's go take a look at addition up here at the top. Very boring. Takes an integer a and b and just returns the total of them. But what if it was more sophisticated? What if it returned a plus half of b so that I could add up the whole array a half at a time? Rather than changing here, I can just use a version of accumulate that works with a lambda. So let's make total 2. And for the last parameter, I'll declare a lambda. Doesn't need to capture anything from local scope. It takes an integer a and an integer b. And returns a plus b divided by 2. If I run this, oh, I should print it out too. That looks roughly half, allowing for rounding. It's really simple to step in and put your own code in how the accumulation goes forward.